A turbocharger, or turbo, from Greek tau upsilon rho beta eta, is a turbine-driven forced induction device that increases an internal combustion engine's efficiency and power output by forcing extra air into the combustion chamber. This improvement over a naturally aspirated engine's power output is because the compressor can force more air and proportionately more fuel into the combustion chamber than atmospheric pressure alone. Turbochargers were originally known as turbosuperchargers when all forced induction devices were classified as superchargers. Nowadays the term supercharger is usually applied only to mechanically driven forced induction devices. The key difference between a turbocharger and a conventional supercharger is that a supercharger is mechanically driven by the engine, often through a belt connected to the crankshaft, whereas a turbocharger is powered by a turbine driven by the engine's exhaust gas. Compared to a mechanically driven supercharger, turbochargers tend to be more efficient but less responsive. Twin-charger refers to an engine with both a supercharger and a turbocharger. Turbochargers are commonly used on truck, car, train, aircraft, and construction equipment engines. They are most often used with Otto cycle and diesel cycle internal combustion engines. They have also been found useful in automotive fuel cells. History. Forced induction dates from the late 19th century, when Gottlieb Daimler patented the technique of using a gear-driven pump to force air into an internal combustion engine in 1885. The turbocharger was invented by Swiss engineer Alfred Bucci, the head of diesel engine research at Gebruder Sulzer engine manufacturing company in Winterthur, who received a patent in 1905 for using a compressor driven by exhaust gases to force air into an internal combustion engine to increase power output. But it took another 20 years for the idea to come to fruition. During World War I, French engineer Auguste Rateau fitted turbochargers to Renault engines powering various French fighters with some success. In 1918, General Electric engineer Sanford Alexander Moss attached a turbocharger to a V-12 Liberty aircraft engine. The engine was tested at Pikes Peak in Colorado at 14,000 feet to demonstrate that it could eliminate the power loss usually experienced in internal combustion engines as a result of reduced air pressure and density at high altitude. General Electric called the system turbo-supercharging. At the time, all forced induction devices were known as superchargers. However, more recently the term supercharger is usually applied to only mechanically driven forced induction devices. Turbochargers were first used in production aircraft engines such as the Napier Lioness in the 1920s, although they were less common than engine-driven centrifugal superchargers. Ships and locomotives equipped with turbocharged diesel engines began appearing in the 1920s. Turbochargers were also used in aviation, most widely used by the United States. During World War II, notable examples of U.S. aircraft with turbochargers include the B-17 Flying Fortress, B-24 Liberator, P-38 Lightning, and P-47 Thunderbolt. The technology was also used in experimental fittings by a number of other manufacturers, notably a variety of Focke-Wulf FW190 models. But the need for advanced high-temperature metals in the turbine kept them out of widespread use. Turbochargers are widely used in car and commercial vehicles because they allow smaller capacity engines to have improved fuel economy, reduced emissions, higher power and considerably higher torque. Turbocharging versus supercharging. In contrast to turbochargers, superchargers are mechanically driven by the engine. Belts, chains, shafts, and gears are common methods of powering a supercharger, placing a mechanical load on the engine. For example, on the single-stage, single-speed supercharged Rolls-Royce Merlin engine, the supercharger uses about 150 horsepower, yet the benefits outweigh the costs. For the 150 horsepower to drive the supercharger, the engine generates an additional 400 horsepower, a net gain of 250 horsepower. This is where the principal disadvantage of a supercharger becomes apparent. The engine must withstand the net power output of the engine plus the power to drive the supercharger. Another disadvantage of some superchargers is lower adiabatic efficiency as compared to turbochargers. Adiabatic efficiency is a measure of a compressor's ability to compress air without adding excess heat to the air. Even under ideal conditions, the compression process always results in elevated output temperature. However, more efficient compressors produce less excess heat. Roots superchargers impart significantly more heat to the air than turbochargers. Thus, for a given volume and pressure of air, the turbocharged air is cooler, and as a result denser, containing more oxygen molecules, and therefore more potential power than the supercharged air. In practical application, the disparity between the two can be dramatic, with turbochargers often producing 15% to 30% more power based solely on the differences in adiabatic efficiency. By comparison, a turbocharger does not place a direct mechanical load on the engine, although turbochargers place exhaust back pressure on engines, increasing pumping losses. This is more efficient because while the increased back pressure taxes the piston exhaust stroke, much of the energy driving the turbine is provided by the still expanding exhaust gas that would otherwise be wasted as heat through the tailpipe. In contrast to supercharging, the primary disadvantage of turbocharging is what is referred to as lag or spool time. This is the time between the demand for an increase in power and the turbocharger providing increased intake pressure, and hence increased power. Throttle lag occurs because turbochargers rely on the buildup of exhaust gas pressure to drive the turbine. In variable output systems such as automobile engines, exhaust gas pressure at idle, low engine speeds, or low throttle is usually insufficient to drive the turbine. Only when the engine reaches sufficient speed does the turbine section start to spool up, or spin fast enough to produce intake pressure above atmospheric pressure. A combination of an exhaust-driven turbocharger and an engine-driven supercharger can mitigate the weaknesses of both. This technique is called twin charging. In the case of electromotive diesel's two-stroke engines, the mechanically assisted turbocharger is not specifically a twin charger, as the engine uses the mechanical assistance to charge air only at lower engine speeds and startup. Once above notch number 5, the engine uses true turbocharging. This differs from a turbocharger that uses the compressor section of the turbo compressor only during starting, and, as a two-stroke engines cannot naturally aspirate, and, according to SAE definitions, a two-stroke engine with a mechanically assisted compressor during idle and low throttle is considered naturally aspirated. Operating principle. In normally aspirated piston engines, intake gases are pushed into the engine by atmospheric pressure, filling the volumetric void caused by the downward stroke of the piston, similar to drawing liquid using a syringe. The amount of air actually inspirated, compared to the theoretical amount if the engine could maintain atmospheric pressure, is called volumetric efficiency. The objective of a turbocharger is to improve an engine's volumetric efficiency by increasing density of the intake gas, allowing more power per engine cycle. The turbocharger's compressor draws in ambient air and compresses it before it enters into the intake manifold at increased pressure. This results in a greater mass of air entering the cylinders on each intake stroke. The power needed to spin the centrifugal compressor is derived from the kinetic energy of the engine's exhaust gases. A turbocharger may also be used to increase fuel efficiency without increasing power. This is achieved by recovering waste energy in the exhaust and feeding it back into the engine intake. By using this otherwise wasted energy to increase the mass of air, it becomes easier to ensure that all fuel is burned before being vented at the start of the exhaust stage. The increased temperature from the higher pressure gives a higher Carnot efficiency. The control of turbochargers has changed dramatically over the 100+ years of its use. Modern turbochargers can use wastegates, blow-off valves and variable geometry, as discussed in later sections. The reduced density of intake air is often compounded by the loss of atmospheric density seen with elevated altitudes. Thus, a natural use of the turbocharger is with aircraft engines. As an aircraft climbs to higher altitudes, the pressure of the surrounding air quickly falls off. At 18,000 feet, the air is at half the pressure of sea level, which means that the engine produces less than half power at this altitude. Pressure increase in automotive applications. Boost refers to the amount by which intake manifold pressure exceeds atmospheric pressure. This is representative of the extra air pressure that is achieved over what would be achieved without the forced induction. The level of boost may be shown on a pressure gauge, usually in bar, psi, possibly kPa. In aircraft engines, turbocharging is commonly used to maintain manifold pressure as altitude increases. Since atmospheric pressure reduces as the aircraft climbs, power drops as a function of altitude in normally aspirated engines. Systems that use a turbocharger to maintain an engine's sea-level power output are called turbo-normalized systems. Generally, a turbo-normalized system attempts to maintain a manifold pressure of 29.5 inches of mercury. In petrol engine turbocharger applications, boost pressure is limited to keep the entire engine system, including the turbocharger, inside its thermal and mechanical design operating range. Overboosting an engine frequently causes damage to the engine in a variety of ways, including pre-ignition, overheating, and overstressing the engine's internal hardware. For example, to avoid engine knocking and the related physical damage to the engine, the intake manifold pressure must not get too high. Thus, the pressure at the intake manifold of the engine must be controlled by some means. Opening the wastegate allows the excess energy destined for the turbine to bypass it and pass directly to the exhaust pipe, thus reducing boost pressure. The wastegate can be either controlled manually or by an actuator. Turbocharger lag. Turbocharger lag is the time required to change power output in response to a throttle change. Noticed as a hesitation, a slowed throttle response when accelerating as compared to a naturally aspirated engine. This is due to the time needed for the exhaust system and turbocharger to generate the required boost. Inertia, friction, and compressor load are the primary contributors to turbocharger lag. Superchargers do not suffer this problem because the turbine is eliminated due to the compressor being directly powered by the engine. Turbocharger applications can be categorized into those that require changes in output power and those that do not. While important to varying degrees, turbocharger lag is most problematic in applications that require rapid changes in power output. Engine designs reduce lag in a number of ways: lowering the rotational inertia of the turbocharger by using lower radius parts and ceramic and other lighter materials, changing the turbine's aspect ratio, increasing upper deck air pressure and improving wastegate response. reducing bearing frictional losses, e.g., using a foil bearing rather than a conventional oil bearing, using variable nozzle or twin-scroll turbochargers, decreasing the volume of the upper deck piping, using multiple turbochargers sequentially or in parallel, using an anti-lag system, using a turbocharger spool valve to increase exhaust gas flow speed to the turbine. Boost threshold. The boost threshold of a turbocharger system is the lower bound of the region within which the compressor operates. Below a certain rate of flow, a compressor produces insignificant boost. This limits boost at a particular RPM, regardless of exhaust gas pressure. Newer turbocharger and engine developments have steadily reduced boost thresholds. Electrical boosting is a new technology under development. It uses an electric motor to bring the turbocharger up to operating speed quicker than possible using available exhaust gases. An alternative to e-boosting is to completely separate the turbine and compressor into a turbine generator and electric compressor as in the hybrid turbocharger. This makes compressor speed independent of turbine speed. In 1981, a similar system that used a hydraulic drive system and overspeed clutch arrangement accelerated the turbocharger of the MV Canadian Pioneer. Turbochargers start producing boost only when a certain amount of kinetic energy is present in the exhaust gases. Without adequate exhaust gas flow to spin the turbine blades, the turbocharger cannot produce the necessary force needed to compress the air going into the engine. The boost threshold is determined by the engine displacement, engine RPM, throttle opening, and the size of the turbocharger. The operating speed at which there is enough exhaust gas momentum to compress the air going into the engine is called the boost threshold RPM. Reducing the boost threshold RPM can improve throttle response. Key components. The turbocharger has three main components: the turbine, which is almost always a radial inflow turbine; the compressor, which is almost always a centrifugal compressor; the center housing, hub rotating assembly. Many turbocharger installations use additional technologies, such as wastegates, intercooling and blow-off valves. Turbine energy provided for the turbine work is converted from the enthalpy and kinetic energy of the gas. The turbine housings direct the gas flow through the turbine as it spins at up to 250,000 revolutions per minute. The size and shape can dictate some performance characteristics of the overall turbocharger. Often the same basic turbocharger assembly is available from the manufacturer with multiple housing choices for the turbine, and sometimes the compressor cover as well. This lets the balance between performance, response, and efficiency be tailored to the application. The turbine and impeller wheel sizes also dictate the amount of air or exhaust that can flow through the system, and the relative efficiency at which they operate. In general, the larger the turbine wheel and compressor wheel, the larger the flow capacity. Measurements and shapes can vary, as well as curvature and number of blades on the wheels. A turbocharger's performance is closely tied to its size. Large turbochargers take more heat and pressure to spin the turbine, creating lag at low speed. Small turbochargers spin quickly but may not have the same performance at high acceleration. To efficiently combine the benefits of large and small wheels, advanced schemes are used such as twin turbochargers, twin-scroll turbochargers, or variable geometry turbochargers. Twin turbo or bi-turbo designs have two separate turbochargers operating in either a sequence or in parallel. In a parallel configuration, both turbochargers are fed one half of the engine's exhaust. In a sequential setup, one turbocharger runs at low speeds and the second turns on at a predetermined engine speed at load. Sequential turbochargers further reduce turbo lag, but require an intricate set of pipes to properly feed both turbochargers. Two-stage variable twin turbos employ a small turbocharger at low speeds and a large one at higher speeds. They are connected in a series so that boost pressure from one turbocharger is multiplied by another, hence the name two-stage. The distribution of exhaust gas is continuously variable, so the transition from using the small turbocharger to the large one can be done incrementally. Twin turbochargers are primarily used in diesel engines. For example, in Opel bi-turbo diesel, only the smaller turbocharger works at low speed, providing high torque at 1,500 to 1,700 revolutions per minute. Both turbochargers operate together in mid-range, with the larger one pre-compressing the air, which the smaller one further compresses. A bypass valve regulates the exhaust flow to each turbocharger. At higher speed only the larger turbocharger runs. Smaller turbochargers have less turbo lag than larger ones, so often two small turbochargers are used instead of one large one. This configuration is popular in engines over 2,500 cc and in V-shape boxer engines. Twin-scroll or divided turbochargers have two exhaust gas inlets and two nozzles. A smaller, sharper angled one for quick response and a larger, less angled one for peak performance. With high-performance camshaft timing, exhaust valves in different cylinders can be open at the same time, overlapping at the end of the power stroke in one cylinder and the end of exhaust stroke in another. In twin-scroll designs, the exhaust manifold physically separates the channels for cylinders that can interfere with each other, so that the pulsating exhaust gases flow through separate spirals. With common firing order 1, 3, 4, 2, two scrolls of unequal length pair cylinders 1 to 4 and 3 to 2. This lets the engine efficiently use exhaust scavenging techniques, which decreases exhaust gas temperatures and NOx emissions, improves turbine efficiency, and reduces turbo lag evident at low engine speeds. Variable geometry or variable nozzle turbochargers use movable vanes to adjust the airflow to the turbine, imitating a turbocharger of the optimal size throughout the power curve. The vanes are placed just in front of the turbine like a set of slightly overlapping walls. Their angle is adjusted by an actuator to block or increase airflow to the turbine. This variability maintains a comparable exhaust velocity and back pressure throughout the engine's rev range. The result is that the turbocharger improves fuel efficiency without a noticeable level of turbocharger lag. Compressor. The compressor increases the mass of intake air entering the combustion chamber. The compressor is made up of an impeller, a diffuser and a volute housing. The operating range of a compressor is described by the compressor map. Portage shroud. The flow range of a turbocharged compressor can be increased by allowing air to bleed from a ring of holes or a circular groove around the compressor at a point slightly downstream of the compressor inlet. The portage shroud is a performance enhancement that allows a compressor to operate at significantly lower flows. It achieves this by forcing a simulation of impeller stall to occur continuously. Allowing some air to escape at this location inhibits the onset of surge and widens the operating range. While peak efficiencies may decrease, high efficiency may be achieved over a greater range of engine speeds. Increases in compressor efficiency result in slightly cooler intake air, which improves power. This is a passive structure that is constantly open. The ability of the compressor to provide high boost at low RPM may also be increased marginally. Portage shrouds are used by many turbocharger manufacturers. Center housing, hub rotating assembly. The center hub rotating assembly houses the shaft that connects the compressor impeller and turbine. It also must contain a bearing system to suspend the shaft, allowing it to rotate at very high speed with minimal friction. For instance, in automotive applications, the CHRA typically uses a thrust bearing, a ball bearing lubricated by a constant supply of pressurized engine oil. The CHRA may also be considered water-cooled by having an entry and exit point for engine coolant. Water-cooled models use engine coolant to keep lubricating oil cooler, avoiding possible oil coking from the extreme heat in the turbine. The development of airfoil bearings removed this risk. Ball bearings designed to support high speeds and temperatures are sometimes used instead of fluid bearings to support the turbine shaft. This helps the turbocharger accelerate more quickly and reduces turbo lag. Some variable nozzle turbochargers use a rotary electric actuator, which uses a direct stepper motor to open and close the vanes, rather than pneumatic controllers that operate based on air pressure.